Assalamualaikum. We are from Group 15 are going to present our project. Our project title is Design Improvement and Analysis of Aircraft Engine Bracket. First of all, I would like to introduce myself. My name is Muhammad Zulkarnain, and my other two members is Muhammad Haikal and Muhammad Labib Toha. Here is our table of content. We have 12 different of subtopic in our slide. First is our introduction. Aircraft engine bracket holds the engine cowling during maintenance. Its original material is titanium alloy. It is very strong but energy intensive. Our aim is to redesign bracket using alternative materials such as aluminium to improve sustainability. We have four main objectives in this project. First, reduce bracket mass to less than 0.8 kg. Second, maintain structural strength and integrity. Third, use CAD and CAE tools for analysis. Fourth, support SDG 12, responsible consumption and production. Here is our methodology overview. We are using softwares like CATIA V5 for modeling and ANSYS Workbench for analysis. We have three key analyses. First, linear static analysis. Second, thermal stress analysis. And fourth, free vibration model analysis. Our target specs is factor of safety is more than 1.2. Total deformation is less than 0.35 mm. Our mass is less than 0.8 kg. Here is our types of design. During our project, there is 4 design we chose among all. All of these design meet all the target specification. Design 1 is Design J. Design 2 is Design K. Design 3 is Design N. Design 4 is Design O. So, for our final design, we have chosen Design O. We are using material such as aluminium. Its mass is 0.77188 kg. Factor of safety is 1.3205. The value of total deformation is 0.28655 mm. Our equivalent von Mises stress is 212.04 MPa. It is chosen for best balance of weight, strength, and safety.
So the total deformation as shown in the image, the total deformation result for design O is 0.28655 mi, aligned with the finding deformation. Confirmation is stay within the 0.35 mm limit under static load. For the equivalent bond mean stress, the bond mean stress value in the image is crystal clear with the information in the report. Thermostat result is 1279.4 MPa. To the latter, acid yield strength due to the temperature effect. For the mass compression, design O mass is 0.77 kg. So it match in the report that we find optimal value of 0.77188 kg, meeting the sub of the target is 0.8 kg. For the factor of safety for S, in the image list of 1.3 for the tropa and routine, but in the result, thermal analysis reveal it a critical drop to 0.22 under heat, underscoring the need for design improvement. So the data consistency is discrepancy deformation value is 0.0665 mm versus 0.2865 mm in the information. Mass stem from different load conditions, static versus thermal. So this is the introduction of thermal stress analysis. Thermal stress analysis evaluate how the aircraft engine bracket perform under temperature change, simulating real-world condition near the engine. This analysis is critical because the bracket is exposed to temperature up to 175 Celsius, which can significantly impact in structure integrity. Cause of a thermal stress, aluminium high thermal expansion coefficient cause the bracket to expand, but feed support constrained with movement creating internal stress. Stress concentrate at the top hole and base where mechanical load and thermal expansion interact. The implication, without design change, repeat thermal cycle could lead uh, to, to venticate crack or permanent deformation in surface. The result highlight a gap between static and thermal performance, emphasizing the need for thermal aware design. So my recommendation, to mitigate thermal stress, we propose flexible joint to allow expansion or high temperature alloy like 2680A aluminum. Thermal insulation or coating could also reduce heat transfer to the bracket. So the conclusion, while the bracket meets static requirement, thermal analysis reveal critical vulnerabilities that must be addressed for the real world safety. In future, the work must should focus on material selection and geometry optimization to improve thermal performance. For research safety verification, the design O is the bracket natural frequency is 2979.6 Hz, significantly higher than the engine 275.8 Hz. Excitation frequency matching with the information that we need to the design avoid resonance risk. For the mode and shape deformation, peak deformation of 88.792 mm in the mode 3 align with the align with the point that we need, highlighting area needing potential reinforcement despite resonance safety. For the tabula consistent, the tabular frequency and deformation in the image directly reflect with the information free vibration result section 5.0 in the validating NC simulation. Design application is all mode are safe from the resourceness. And the height deformation in mode 3 is 88.792 mm and 5 and mode 5 is 75.462 mm. Suggest stiffness adjustment could further optimize dynamic performance. For the gap breaking, the upcoming mode shape in the image will visually supplement into the point that contemplate clarifying deformation pattern at each frequency. For the mode 1, it has 2979.6 Hz, likely show the bracket fundamental bending mode in the simple deformation pattern. Correspond to 68.029 mm max deformation in the information. Visualize where the bracket flex most under vibration. Mode 2 is 4633.6 Hz, probably display torsional or secondary bending. 55.082 mm deformation suggest reference stress distribution than mode 1. Mode 3 is 6363.6 Hz, expected to show complex combined bending. 88.729 mm deformation often highlight weak areas needing reinforcement. For the modes 4 until 6 is 8026.2 until 1490 Hz. Highest frequency mode with the locally deformation, for example, is 93.333 and 43.969 mm. Reveal how specifically section like mounting hole vibration. All mode frequency are far above the engine. No, doesn't have resonance risk. So the visualization confirm from the point simulation data if frequency and deformation value are requirement and get it.
Okay, now it's time for discussion part. So, why use design O? Because the design O was selected due to like the weight and acceptable safety margin. Also, the best deformation performance. And also for the material itself, is a got a we use aluminum where it's got a lot of advantages. It is lightweight, good missionability, corrosion resistant, affordable and recyclable. Now, for the recommendation part, first one we want to improve is the thermal resistance, where we add a thermal insulation to limit heat impact, and also using the coating or material with higher thermal strength. Second, we optimize the geometry for the thermal loads, modify design to allow controlled thermal expansion by reducing the concentration at the sweet support. And also number three is thermal material consideration, where we explore more hybrid material or heat resistant alloy. Also, we consider aluminum alloy with a better high temperature properties. This one is the last part for this presentation, where for the conclusion is for our project. So the redesigned aircraft engine bracket is lighter and strong enough to handle the load with the no, handle the normal loads safely. It meet the design goals for the strength deformation and sustainability. The vibration analysis show that the bracket is safe from resonance. However, the thermal analysis revealed that the bracket is not suitable for the high temperature in its current form. Overall, the project was successful, but the further improvement are needed to handle the thermal condition better. That's all from us. Thank you.